Basic in every radio installation is the vacuum tube. Produced in a wide variety of sizes and types, the vacuum tube is the fundamental element in modern radio communication. Radio utilizing these remarkable tubes makes possible effective communication between the air and ground forces. This symbol represents the triode tube with its elements: the plate, filament, and control grid. The cathode may be equipped with an indirect heater. Between cathode and plate is the grid, which is the characteristic element of the triode tube. It serves as a control of the electron flow between cathode and plate. Remove the glass bulb from a triode tube, and the plate becomes visible. Inside the plate, the grid and filament are located, supported by wires embedded in the glass base. This type of tube is equipped with a directly heated cathode. The control grid is seen wound around outside the cathode. In the diode tube, many electrons leaving the cathode move about between cathode and plate, constituting space charge. The triode tube differs from the diode in containing an element known as the control grid, located between cathode and plate. With the grid positive, many electrons pass from cathode to plate. If the grid is given a negative charge, it repels the negative electrons and fewer of them reach the plate. The grid bias may be so strongly negative as to entirely stop the flow of current through the tube. This negative grid bias, beyond which there is no current flow from cathode to plate, is known as the cutoff bias. The grid thus serves to control electron flow from a heated cathode to the positively charged plate. This circuit represents a hookup to test the effect of grid bias on plate current. With the grid negative well below the cutoff point and the plate positively charged by the B battery, no current is seen to flow around the plate circuit and through the milliammeter. We may chart the flow of plate current with changes in grid bias. The C battery is impressing a minus 20 volts upon the grid. Both the milliammeter and the chart represent no plate current flowing. A grid bias of minus 20 is the cutoff bias of this tube. Now, if we change the grid bias to a minus of 10 volts, the milliammeter indicates 1 unit of current flow in the plate circuit. The arrow on the plate current graph moves up a corresponding distance. If the grid bias is made still more positive, plate current increases. We move the arrow further up on the plate current curve. A still more positive grid results in still greater plate current. Another increase in positive grid voltage leads to the saturation of the tube. A narrow range of grid voltage is thus seen to control the entire output of the tube, extending from zero plate current to the tube's maximum output. This is why the grid is called the control grid. The controlling action of a radio tube results in the tube often being referred to as a valve. This hookup shows grid voltage change in relation to plate voltage change. With a bias of minus 5 volts on the grid and the plate impressed by 100 volts, the milliammeter shows a plate current of 2 units as electrons flow from cathode to plate. The grid contains many electrons constituting a negative charge, which limits the movement of electrons from cathode to plate. The grid thus controls current flow. If we change the grid bias from -5 to -3 volts, the milliammeter shows a plate current rise to 3.5 units. A change of but 2 volts in the grid bias has resulted in increasing plate current to near its maximum. In other words, a small change in grid voltage leads to a large change in plate current. Plate voltage change affects plate current. With -5 volts on the grid and 100 volts on the plate, the milliammeter shows 2 units of current as before. Now a plate increase of 35 volts is necessary to increase plate current to 3.5 units. Now if we change grid bias by only 4 volts, a very great change is seen in plate current. We conclude that the greatest influence on the tube output is change in grid voltage. Most military sets use some form of the triode tube. By hooking a transformer to a triode tube circuit, energy may be transferred to another circuit. The tube is connected to a B battery, a C battery, and an alternator. The alternator varies the voltage to the grid. The plate current passing through the primary of the transformer induces a corresponding current in the secondary at the transformer. When the circuit is made to function, electrons pass from cathode to plate when the grid is plus, the flow of current stopping when the grid is strongly minus. The alternator impresses a voltage wave upon the grid. The wave of current in the secondary of the transformer has the same frequency and wave shape as the grid voltage wave. It is of greater magnitude, however. In other words, it is an enlarged replica of the input voltage wave. Thus, the triode tube is an amplifier in that it magnifies a wave without changing its shape. Modern receiving sets of great efficiency owe their effectiveness to the ability of the vacuum tube to amplify waves of voltage and current. Some of these tubes are very small, outstanding examples of scientific engineering. The simple triode tube is actually a complicated electric condenser having 3 capacitances to be considered. They are cathode to grid, plate to grid, and plate to cathode. The capacitance, of most importance, exists between grid and plate. This capacitance may produce undesired coupling between the input and output circuits. To shield the control grid, another grid known as the screen grid may be added to the triode tube. A condenser connects the screen grid to the cathode circuit. This bypass condenser enables the screen grid to electrically isolate the plate and control grid. The simple triode tube contains but the 3 elements: plate, grid, and cathode. The principal electron flow in the tube is from cathode to plate. Electrons reaching the plate at high velocity strike other electrons, knocking them off the plate. This is known as secondary emission. The introduction of the screen grid adds another positive element in the tube, which may attract electrons. Paths of electrons of secondary emission cut across the screen grid. These electrons coming from the plate cause an undesirable plate-to-screen current. A third grid may be placed between plate and screen grid. This grid is known as the suppressor grid. Electrons flow freely through all three grids, but the paths of secondary emission are shortened by the negative suppressor grid. As a result, the emitted electrons due to electronic bombardment do not extend as far as the screen grid. The pentode tube represents the highest development of the triode principle. Tetrode and pentode tubes are made in many sizes and capacities. Multiple contacts leading to the tube elements characterize these tubes in their many forms. Although their internal construction may vary widely. The older and somewhat bulky military receivers using earlier types of tubes have been superseded by sets much smaller in size. The greater compactness and efficiency of these sets is largely due to their use of the modern pentode tube. The suppressor grid between the screen grid and the plate in the pentode may be omitted. Instead, what is known as beam-forming plates are substituted. This is the symbol for the beam power output tube. This tube is built with the usual cathode, grid, screen, and plate. The beam-forming plates are so placed as to direct the cathode-to-plate stream of electrons in a beam. Here the stream of electrons carry the secondary electrons, which are knocked off, back to the plate, thereby eliminating the necessity for a suppressor grid. Whether built into great power tubes or into the tiny peanut tube, the principles of the triode tube are basic.